Good evening, my YouTube viewers. Crystal here. I wanted to make another video for you because what I've done is I've done some more experimentation, and basically what I've done is I've tried to make predictions on the E. coli data set with the PCA. And what I'm going to do is I'm going to go over the program that I wrote with you, and at the very end I'll give you the answer. I will tell you what the result was when I tried to make the predictions on the E. coli data set using PCA. So the first thing we're going to do is I've got my program on a repository and my personal GitHub account, and whenever I make the blog post, I'll give you the link to the blog post so you can actually go onto the program and look at it. But the first thing we'll do, and then I just wanted to say that I wrote this on Google Colab because Google Colab has most of the libraries already installed. So after I've stated that, what we'll do is we'll talk about the E. coli imbalance dataset. So the dataset describes the problem of classifying E. coli proteins using their amino acid sequences and their cell localization sites. That is, predicting how a protein will bind to a cell based on the chemical composition of the protein before it is folded. The dataset is credited to Kenta Nakai and was developed into its current form by Paul Horton and Kenta Nakai in their 1996 paper titled A Probabilistic Classification System for Predicting the Cellular Localization Sites of Protein. In it, they achieved classification accuracy of 81%. The dataset is comprised of 335 examples of E. coli proteins, and each example is described using 7 input variables calculated from the protein's amino acid sequence. And then they tell you what the sequences are and what the names of the classes are, and I won't go into that. I'll just leave that for you to read on your own. And then so I imported my libraries, which are already installed on Google Colab. I imported Pandas, NumPy, Matplotlib, and Seaboard. And then I loaded the E. coli dataset, and because the E. coli dataset did not have any labels, did not have any columns, I had to define the columns. So now you can see the dataset with the columns already defined. So I checked for any null values, and in this instance, we did not have any null values. So what I did was I compared the result with the independent variables. So we compared the dependent variables with the independent variables so you can see what they are right there. I didn't label and call the result. I just, the original program had been label encoded, but I took the label encoding out. I just didn't take out the little text message that said we were label encoding it, but we're not label encoding it anymore. So the results are not label encoded. They're the way they're supposed to be. And so what we did was we did a heat map so you can see how the independent variables affect the dependent variable. And if you're really into heat maps and you know how they work, then that's something good to look into. So then what we did was we counted the classes. So we had 8 classes, I believe. 1, 2, 3, 4, 5, 6, 7, 8. And then we talked about the percentage that was in each class. And so on 2 of the classes, we had like 0.5%. So it was really difficult for the program, the model, to pick up these 2 classes that were less than 1%. They were even less than 0.6%. So we wanted to see what percentage was in the result, so you can see that very clearly. So we did a group by, so you can see again how many you had examples of each, how many examples you had of each class. So we did a percentage of the result again, so you can see that again. And now what we've done is we have done a graphical representation of the variables. So if you like graphs and you like analyzing them, then this will give you some good information about the graphical depiction of each column. So we have assigned our X and our Y values in this program. So Y is train.result and X is train.result. Axis equals 1. And so you can see the X shape and the Y shape. So your X shape is 335 of 7 columns, and your Y shape is 1 column of 335. It's an array. So now what we do is we split our training set up for testing and validation. Or really what we're doing is we're splitting X up. So X train, X val, Y train, Y val equals train test split, X, Y, random state equals 0, test size equals 50%, stratify equals yes, and shuffle equals true. And then we check our the shape of our data sets created as well. So we also put the data sets on a scalar. So scalar equals standard scalar fit X train. X train equals scalar dot transform X train. And X val equals scalar dot transform X val. So now what we're going to do is we're going to apply the PCA. And PCA is like principal component analysis, I believe. And I tested every single component. I tested all components from 1 to 7. And I did not get an improvement of the prediction on any of those components. And the reason why you're seeing components equal 7 is because that's the last digit that I tested PCA on. So PCA is a fit transform function as well. So X train equals PCA fit transform X train, and X val equals PCA transform X val. So we do count our values on the validation set, so you can see how many values you have of everything. And we've got all 8 classes represented. And then we set class weights, even though I didn't use class weights in this particular program. I went ahead and kept class weights in there just in case I need it for something else. So because CatBoost is not already installed on Google, we had to install CatBoost on Google. And then after we installed CatBoost on Google, we imported CatBoost classifier, and then we set up our function, or set up our model. So CT model equals CatBoost classifier, loss function equals multi-class, class weights, and then we go into the class weights, which I have previously discussed in a previous blog post in a previous video. But what you do is you take the percentage of the class and you subtract it from 1, and that's your result. So on the first class, it had 42%. So 1 minus 42% is 58%. And then you do that for all 8 classes. So we have iterations of 300, depth equals 5, random state equals 1. We fit it, X train, Y train, and then we print our accuracy. So we go down here. And we had an accuracy of 100%, so you can't get much better than that. And we predicted on the model after we applied PCA to it, and we had exactly the same that we had when we didn't have any PCA. But I will say that when the components were less, the model was a lot worse. The accuracy was a lot worse when we had less components. Put it on a counter, and then we put it on a confusion matrix, and you can see that 2 and 3 are not represented. So the model did not pick up any examples from 2 or 3. So now we go to random forest. We set up random forest to predict on it, and we set it up, and we had an accuracy of 100%. And when we predicted on the validation set, we had an accuracy of 88.69%, which was exactly the same as what we had when we didn't have any PCA. And I will say that what I did was, whenever I was applying PCA, I went from 1 to 7, and I did not get an improvement on my accuracy on any of those values. And so we've got a confusion matrix. So you can see on this confusion matrix, you can see again that 2 and 3 are not represented. They were not picked up by the model, and we've counted that. So that concludes this presentation, and that just tells you that in this particular instance, PCA did not improve the accuracy of the E.Coli dataset, but I'm going to try PCA on the Titanic dataset and see if it improves the accuracy on the Titanic dataset. So thank you so much for watching this video, and I look forward to making other videos for you. If you like my work, please like, subscribe, and share. If you like the work I do and want to leave a donation, I've got my email address for my PayPal account in the description box down below, because I don't have enough subscribers to monetize. Thank you very much.